Hello and welcome to today's lecture on minimizing leakage power. In the last lecture, we have started our discussion on how leakage power can be minimized, and we have discussed some of the techniques by which you can minimize standby leakage power, such as transistor stacking, variable threshold voltage CMOS known as VT CMOS, and then multi threshold voltage CMOS MT CMOS. This MT CMOS approach has now become very matured, and nowadays it is also called power gating. Today I shall discuss about this approach in detail, and in my next lecture we shall continue with other techniques for leakage power minimization. So, here is the agenda of today's lecture. After giving brief introduction about power gating, I shall discuss about clock gating versus power gating, and then various issues related to power gating, such as granularity levels, topologies, impact of power gating on different class of subsystems, then switching fabric design, isolation strategy, retention strategy, and then I shall end my lecture with power gating controller. I have already discussed how the multiple threshold voltage transistor, transistors of multiple threshold voltages are used to minimize leakage power. We have seen we can add two slip transistors. One is this header transistor PMOS, and another is NMOS transistor, which is known as footer transistors, and these are of high threshold voltage, and the original circuit is realized by using low voltage CMOS transistors. So, this is how it is being done. This is also known as MT CMOS power gating. Why is it called power gating? As you can see, essentially what we are doing, we are getting the supply voltage with the help of these high threshold voltage transistors. Normally, we do gating to stop clock, known as clock gating, and there we have seen the clock is not allowed to reach the circuit, either resistors or combinational circuit, so that the switching activity is reduced. But in this case, what you are doing, we are getting power supply. How can it be done? Obviously, we have to put a switch in between power supply. So, you have got your VDD, and then we will put a switch, and the output of the switch will go to the circuit, and the other end may be grounded. So, question naturally arises, how do we really realize this switch? Actually, the switch is realized with the help of a PMOS transistor of high threshold voltage. So, this is the PMOS transistor switch, that is used in series with this circuit. So, switch is realized with the help of a PMOS transistors. That is exactly what is being done here. You may be asking, why do we put a high VT PMOS transistors? The reason for that is, as we know, our main intention is to reduce leakage power. The dynamic power can be reduced by using clock gating, but here we are interested in reducing leakage power, and obviously leakage power can be reduced only when the threshold voltage of the transistor is high, and that is the reason why the transistor that is being used in this switch, in realizing this switch, is a PMOS transistor having high VT. And and that is the reason why this approach is also called MT CMOS based power gating, and subsequently this MT CMOS based part have been removed, and it is simply called power gating. And with the help of this power gating, what essentially we are doing is power management. What is the objective of power management? Objective of power management, what do you really mean by management? Management means sometimes you will follow an approach by which the leakage power can be reduced. How you are going to do that? We shall be turning on some parts of the subsystems and turning on off some parts of the subsystems at appropriate time in a appropriate manner. That is your management. So, that is the job of the management, and in fact, this power gating is precisely done in this way. That means, you are essentially doing power management by getting the supply voltage, and that is the reason why it is also called power management. So, the same thing is being told when same thing is being done whenever you do empty CMOS based power gating or power management. So, any of the three actually means the same thing. Now, let me start our discussion with this clock gating versus power gating. So, here as you can see, whenever you do clock gating in this part, this dynamic power is reduced, but leakage power remains the same. So, leakage power as you can see, in this case neither clock gating is done nor power gating is done. Here only clock gating is done. So, the leakage power is present. So, clock gated leakage power, and so whenever you are in the sleep mode, you are essentially reducing the leakage power by getting the clock. So, you can at different points of time you can do that in this part, and so on. So, from this diagram we find that the leakage power remains same, only dynamic power is reduced when you do clock gating. Now, let us see what happens whenever you do power gating. As you can see here, when you do power gating, not only the dynamic power is reduced, because whenever you when power gating is being done, not only the dynamic power is reduced, not only the clock is gated, the supply voltage is also gated, and as a consequence the dynamic power is reduced and also leakage power is significantly reduced. So, this is the power gated leakage power, and that can happen at different points of time depending on the application. So, this is the activity level 1, and this is the and in this part there is no activity, the circuit can be power gated. Similarly, here activity level 2, activity 2, and again power is turned on, and it is having dynamic power as well as leakage power dissipation, and in this part again power gating is done. So, you have got reduction in leakage power. You may be asking that whenever the supply voltage is isolated, why there should be leakage power dissipation? The reason for that is you are doing power gating using a MOS transistor switch, and MOS transistor switch obviously will have some leakage current. It is not an ideal switch. That means, resistance is not infinite. As a consequence, the leakage power will not become 0, but it will definitely be much less than whenever you do not do power gating. So, compared to power gating, if you do not do power gating, compared to that you can see there is a reduction in leakage power. That is essentially possible because of the use of high VT transistors in series. Okay. So, this is the difference between power gating and this is the difference between clock gating and power gating. Okay. Now, let us come to little bit about the power gating strategy. So, power gating has essentially two modes. One is known as active mode, another is low power mode. So, this active mode means whenever the circuit is in full operation, clock is applied, power supply is applied, and the standby mode or low power mode is when power is gated. So, to switch between these two modes of operation and appropriate time at the appropriate time in an appropriate manner. As I told, power gating is nothing but power management. You have to switch between these two modes at appropriate time in an appropriate manner with this goal. What are the goals? To optimize reduction in power and to minimize impact on performance. So, as I told, the challenge of any power reduction technique is to maintain the performance level same. That means, without reduction or compromise in performance, you have to do the power gating and you have to maximize the reduction in power. So, obviously, as we shall see, this approach affects inter-block interface communication and is more invasive than clock gating. In case of clock gating, we have seen you have to add some additional hardware. However, that additional hardware is not does not make significant difference, and as a result it is not that much invasive. But in this particular case, as we shall see, it will affect the timing and all the characteristics of the circuit. As a consequence, it is more invasive than the clock gating, and it will add significant time delays, and we have to see whenever it enters this from active mode to low power mode, you have to safely enter it and exit from exit power gated mode. So, there is significant time delays to safely enter and exit power gating modes. That means, you cannot really instantly switch from one mode to another mode. It will always involve some delays. You have to do it slowly. Slowly, you have to go from active mode to low power mode, and again you have to come back to the active mode from the low power mode. So, this will involve significant time delays. Now, question naturally arises, if it is a management technique, who is doing the management, who is controlling? There are several possibilities. Number one is by control software to schedule power gating. So, you have to there is a software, it is controlled by software, there is a control software which will do the power gating. That means, maybe that is part of the operating system, which will find out when to do power gating, that means, when to switch from active mode to low power mode and again come back to the active mode. Another part is part of the device driver. So, or OS idle tasks. That means, in this particular case, that operating system knows when a particular subsystem is in idle condition. So, for example, there is a DMA controller. So, the operating system knows when DMA mode of data transfer has to be performed. So, then the device driver of that particular subsystem can be put to low power mode when it is not in use. So, the idle situations can be found out. Another possibility is it can be initiated by hardware timers. So, inside the processor you will find some hardware timers known as timer counters. For example, you want a particular event to occur after certain time, and that time can be programmed, and after that time is over, that timeout is reached and that event is triggered. For example, as you see, whenever some missile is launched and various, for example, even when you are using a TV, you can program it so that it will switch off after certain time. So, this kind of thing can be triggered with the help of hardware timers. And most sophisticated one is to have power management unit. Nowadays, particularly on silicon on chip systems, you have got power management unit. So, that power management unit will perform this task of switching from one particular mode to another particular mode. And so, this control is done in many ways, and obviously, from application to application it will vary. Then whenever you do power gating, there are several trade-offs. The trade-offs are how much leakage power saving you can do by doing power gating, and the entry and exit time. As I told, the entry to the power gated mode will take some finite time. So, you have to there is a trade-off how quickly it can be done and how much power saving can be achieved. Then the energy dissipated in entering and leaving. Later on we shall see whenever you enter a power gating mode, there is some overhead. So, energy dissipated in entering and leaving such leakage power modes, that is that you have to, there is a trade off of that. That means, by not doing power gating, whatever power dissipation is there, that should be larger than energy dissipated in entering and leaving such such leakage saving mode. Then it will again be, there is a trade off between the activity profile. Based on the activity profile, you have to judge whether you will be doing power gating or not. But as we have already seen, it is essentially controlled by two entities, two events. Number one is sleep event, which initiates entry into the power gated mode, and another is wake event, which initiates return to the active mode. So, these two events will trigger or will switch from one mode to the another mode. And as I have told there are a number of power gating issues, such as granularity levels and so on. I shall discuss them one after the other. First, let us focus on granularity levels. The granularity levels can be essentially of three types. First one is fine grained. So, switch is placed locally inside each standard cell, and the switch must be designed to supply worst case current, so that it does not impact performance. That means, suppose you have got a standard cell. Standard cell can be a 2 input NAND gate or a 3 input NAND gate. So, for each of them you can have a power gating circuit, and obviously, in this case you have to, whenever you use power gating circuit, it will have some area overhead, and this area overhead of each cell is quite significant. It can be 2 times to 4 times, and you have to design the switch. Particularly, you have to, since you are inserting some transistors in series, PMOS transistors in series or NMOS transistors in series, you have to choose the width and length in such a way that it can supply worst case current, because larger the width, it will be able to supply more current, but it will occupy larger area. So, this kind of fine grained technique has large area overhead, and that is the reason why coarse grained power gating granularity is used. In such a case, a block of gates has its power switched by a collection of switch cells. That means, you can do kind of clustering. Several gates can be combined together, and a single switch will take the job, will perform the switching from active mode to low power mode and so on. So, and in this case sizing is very difficult, because you do not know exactly which components will be turned off, turned on, and also the current requirements of different gates. So, this in this particular case sizing is more difficult, and however, it has got significantly less area overhead than the fine grained approach, and this is preferred approach because of lesser area overhead. And whenever you use whether fine grained or coarse grained techniques, you have to take care of the inrush current to be controlled to avoid large IR drops. That means, you should not suddenly switch large number of you should not turn on large number of switches, so that there is a power droop. That means, VDD does not drop, leading to glitches and power line problems. So, inrush current has to be controlled, and we shall see later on how it can be done. Okay, so, we have seen two types of granularity that is being used. Now, let us consider the various topologies. There are 3 different topologies. Number is global power gating. So, in this global power gating, this refers to logical topology in which multiple switches are connected to one or more blocks of logic, and a single virtual ground is shared in common among all the power gated logic blocks. So, here you find this is one logic block, this is another logic block, and this is the third logic block. So, all of them are having a single virtual VDD line. So, here is the rather in this particular case it is virtual ground line. So, this is a single virtual ground line, although you have got multiple switches, and this multiple switches is controlled by using a single slip control signal. So, this topology is effective for large blocks in which all the logic is power gated, but is less effective for physical design reasons when logic blocks are small. So, this particular approach is effective when you are using large blocks, and particularly we have seen this can be used when you are using coarse grained technique. So, these granularity and topology are kind of interrelated. So, this particular technique does not apply when there are many different power gated blocks, each controlled by different sleep enabled signals. That means, whenever you have got a large number of blocks which are controlled by a single control signal, only then you can use this kind of topology. Coming to the second technique, which is known as local power gating. In this case, this particular technique refers to logical topology in which each switch singularly gets its own virtual ground connected to its own group of logic. So, in this case, as you can see, this is one block, and this virtual ground is not connected to the virtual ground of block 2. So, there is there is independent virtual grounds for each of the logic blocks. So, this arrangement results in multiple segmented virtual grounds for a single slip domain. So, you note that there is only a single slip control signal. Although there is a single slip control signal, you have got multiple virtual grounds for different blocks of logic. So, this particular technique can be particularly used when you are using this fine grained granularity. For example, you are doing the gate level, the switching is done at gate level. Okay. So, this arrangement results in multiple segmental virtual grounds, as I have told, with a single slip domain. Coming to the third topology, this is known as switch in cell. So, switch in cell may be thought of as an extreme form of logical power gating implementation. So, in this topology, each logic cell contains its own switch transistor. As you can see, this is an inverter. So, this inverter is provided with another additional transistors. Obviously, this will be a transistor with high threshold voltage, which is built in when this inverter is fabricated. That means, you have got kind of standard cells with this kind of built in gating hardware, and each of these standard cells will be having its own gating hardware built in as part of this circuitry. So, each cell is independently is designed separately, and its primary advantages are that the delay calculation is very straightforward. So, delay calculation is very easy because it can be very easily characterized. So, you have got an inverter, and in series with that you have got a switch, that means your high threshold voltage transistors. So, you can very easily calculate the delay of this particular circuit, and so the calculation of the delay is quite easy. So, whenever you do static timing analysis, the static timing analysis can be done very conveniently without much difficulty. However, whenever you use this approach, the area overhead is substantial. So, there is substantial area overhead because each of the standard cells will have its own power gating hardware built in. So, as a consequence, there is no sharing of power gating hardware is taking place. As a consequence, it will have large area overhead. However, timing analysis is very easy and it is easier to implement. Okay. So, this is so much so about the topologies. Now, let us consider impact of power gating for different subsystem. Let us consider a scenario where you have got a cached CPU. That means, you have got a central processing unit with cache memory. As you know, normally your program is residing in the main memory, which is usually outside the processor CPU. Now, you have got a CPU with on chip cache memory. When the CPU is power gated, obviously the cache memory will lose, the information stored in the cache memory will be lost. So, whenever you do wake up time response to an interrupt system has system level implications, because you have to do it will lead to cache misses, and you have to transfer from the main memory to the cache memory, and reloading of cache contents every time may have large time and energy cost. That means, whenever you have got a cache CPU, as you go from active mode to low power mode, that means you do power gating of the CPU, the information will be lost, and then whenever you do the wake up, you have to transfer, or in other words, if you do not transfer, there will be cache misses, and those cache misses will lead to large overhead. And so, there is a trade off between energy saving due to power gating versus energy lost in reloading state, reloading the state of the processor. I mean, that is the which is being stored in these in those cache memories. So, this is one type of environment or one type of scenario. Second is peripheral subsystem. So, peripheral subsystem may have much better, I mean, in this particular case energy profile is much well defined than a CPU. Why it is much more well defined? The reason for that is, here you know that a particular peripheral, can be a programmable I/O like DMA controller, interrupt controller, or some other programmable I/O, parallel programmable I/O, which are used in microprocessors and microcomputer based systems. Those peripheral subsystems have got much well defined energy profile, and in this case you need it needs for higher, I mean need for device driver to explicitly load store key state. You will notice that these programmable I/O devices, may be a DMA controller or an interrupt controller or whatever it may be, will have some resistors which are part of those peripherals or subsystems. Those resistors are to be initialized whenever you make them active. Say this is a DMA controller. So, DMA controller will have some resistors which will hold the size of data to be transferred between memory and the I/O, and also the from which location to which location, I mean which memory location to which memory location data transfer has to be done. Those are loaded in these resistors. That means, and you will require device driver to explicitly load and store key state. That means, whenever you are going from active state to low power state, that means you are putting a DMA controller or an interrupt controller or some other peripheral subsystem to a low power state. Those register contents, if they are having some values, they have to be saved in the registers of the processor, and then as they wake up, you have to transfer those register contents. Question is, who will do that? So, there is a device driver software which has to do that. So, the device driver has to explicitly load and store those key states which are present in these registers. So, the internal arrangement to store state within the additional hardware. So, there is another alternative inside the peripheral subsystem. You can have some built in hardware where those state values, those state conditions, that means content of those registers can be stored. Later on I shall come back to this particular topic, and how we shall see how inside the subsystems you can have built in memory, built in register values where you can store these things. So, there are two alternatives, either you do it with the help of a device driver, or there is some additional hardware as part of those hardware, that means your those device drivers, that means programmable I/O chips. Third situation is multiprocessor systems. So, this multiprocessor system is becoming very popular in the present day context. You can have multiple processors, either they may not be on same chip, that means two separate chips. Two CPUs can be on a single motherboard, or another or more than 2 processors can be on a single motherboard. That is one possibility. Another possibility is that nowadays you can have multiple processors on a single chip, known as cores. Multi-core processors are becoming increasingly popular, 2 core, 4 core and so core. Whatever it may be, it is assumed that a processor is powered down only when it has completed a task and waited for another task to be assigned. So, in a multi-core architecture, there is an operating system which will do the task scheduling, and if you want to save power, what can be done? The task scheduler schedules tasks to a particular processor, and when that task is complete, it can be that particular core or processor can be switched off. That means, you can put it to low power mode. So, power gating of individual CPUs gives very good leakage power reduction. So, in this particular case, depending on the application, your the computation requirement may be different, and whenever it is done with the help of this task scheduler, then a particular task is over. That means, cache is empty when the CPU is vacant clean and reset ready. That means, a particular processor was put to low power condition when it had completed its tasks. So, when it is waken off, the cache is empty, and obviously, there is no need for no need for loading its own status. Automatically, it will load the contents of cache memory as a new task is scheduled to it. So, the number of cores to be power gated and active can be optimized for varying workload conditions. So, the task scheduler can identify by monitoring the workload condition when one or more cores can be put to low power mode, and when they have to waken up depending on the workload condition. So, these are the 3 scenarios I have discussed, and their impact on power gating I have mentioned. Now, coming to switching fabric design, you have 3 alternatives. You can have header switch as it is shown here. That means, you will have a PMOS slip transistor, or you can have a footer switch, which is a NMOS transistors. Obviously, both these switches will have high threshold voltages, or you can have both. So, originally that empty CMOS approach that was proposed by Mutho et al., they proposed both the switches to be present, header switch as well as footer switch. So, there are many authors, some of them claim that both the switches are necessary, and most of them claim that one is sufficient. So, whenever you use both the switches, two such high VT power switches in series with the gate causes a more significant IR drop in the supply as seen by the gates. That means, when you have got 2 switches, quite large amount significant amount of power drop take place, particularly when the supply voltage is getting gradually reduced, and it is now in the range of 1 volt. So, detailed transistor structures are structuring has to be done, and these are highly technology specific. So, this drop, when this IR drop causes increased delays for the gates in the design. So, the switching fabric design is very complex, and you have to do it properly, so that you get the benefit of leakage power reduction technique. So, with the header switch, the internal nodes and the outputs of a power gated block collapse down towards ground when switched off. So, whenever you are using a header switch, that means this switch is turned off, and that means what will happen in that case, this particular line, this particular point, that virtual ground will be very close to the ground voltage. That means, the outputs of the power gated blocks collapse down towards ground when switched off. That means, when it is switched off, this voltage will become very close to the 0 volt, because this will be a virtual ground voltage. Similarly, when a footer switch, you are whenever you are using this is the header, whenever you are using a footer switch, in that particular case, this voltage will gradually move towards VDD. That means, with the footer switch, the internal loads and outputs of a power gated charge towards VDD when switched off. That means, whenever you switch it off, this voltage will gradually charge towards VDD, but switch this up. So, what has been found, as I told, switch the supply rail or ground rather than both. Usually, one of the two switches are used, and particularly header switch is more appropriate when externally controlled. So, later on you will see this power gating is done in two ways. Switch can be external to the processor, external to the chip, or it can be inside the chip. So, there can be a tree like structure. So, whenever outside the chip, this particular approach, this header switch is more appropriate, because in that case this power distribution, particularly that power rail can be distributed in a very systematic way. Okay. So, whenever you are designing the switches, there are several issues involved in the design. Number one is the area cost. As I told that width to length ratio will decide the current that can flow or IR drop. So, there is IR drop constraints, and there is a trade off between the area and the reduction in leakage power, and system architectural issues which I shall discuss little later. It has some impact on various other architectural issues, and another very important thing is switching efficiency consideration. So, whenever you are putting a switch, when it is on, it can pass some current. So, on current is dependent on the width versus length of this device, and whenever you put them off, this off current is dependent on the threshold voltage and various other parameters. So, this on to off ratio, this I on to I off, this ratio is very important, and it depends on the gate length, width and body bias, which essentially controls the threshold voltage. So, the switching efficiency is known as ION versus IOF, that means on current versus off current, and obviously, this on current versus off current will be different for different types of switches. So, for PMOS transistors, this on current versus off current will be of one type, and for NMOS transistors, this on current versus off current will be of different type. So, this switching efficiency you have to consider whenever you will be designing these power switches. Coming to the different styles of power switch, as you have already seen, whenever we are using a switch, essentially a single switch is not used, a single transistor is not used, a large more than one transistor is usually used. Now, how we will put these transistors? And there are two basic topologies. One is known as ring style. So, here you can see the switches are placed external to power gated block by encapsulating it by a ring of switches. So, you have got a ring of switches, and here is the power gated block. So, these switches connect VDD to the virtual VDD of the power gated block, and this is the only style that can be used to supply power to existing hard block. So, normally you may be using hard IP core. So, whenever you are using a hard IP core, maybe a CPU or some memory or some special purpose processor, whatever it may be, whenever you are using a hard IP core, in such a case this is the only technique that can be used, and it is suitable when retention resistors are used. So, later on I shall discuss about these retention resistors which are necessary to save the state of these power gated block, and later on we shall discuss about it. Then another style is grid style. So, in this case the switches are distributed throughout the power gated region. So, here you can see this is the supply voltage, and this is the this is one virtual VDD. So, this will go to one part of the circuit, this will go to another part of the circuit, this will go to another part of the circuit. So, this is how the power rail is distributed throughout the power gated region. However, you can use a kind of hybrid style where you will be using this ring style as well as this grid style. So, grid style at the top level. So, you will use this in the top level, that means you whenever you are using a hierarchical style, then at the top level you will be using this grid style, and then at lower level you will be using the other style, that is your ring style. So, grid style at the top level, ring style to certain power gated macros or hard IP cores. So, this is how you can combine both the ring and grid style the switches in your hardware, in your circuitry. Now, coming to a very important issue, that is your known as signal isolation. What do you really mean by signal isolation? To illustrate the need for signal isolation, let us consider a power gated block. So, the power gating is done with the help of a slip transistor header switch, which is connected here. So, here is your virtual VDD. Now, as I mentioned, whenever you turn this switch off, this voltage is supposed to rise to VDD. Sorry, this voltage is supposed to go where to reach the ground level. So, in this particular case, it discharges through this path because of larger current of this power gated block. So, the outputs of power gated down blocks may result in power over current in the powered up blocks. So, what can happen? You cannot really guarantee that this voltage will be discharged to ground level, or whenever you are using a footer switch, this voltage will charge to VDD level. This you cannot guarantee, because it will depend on the relative value of the leakage current of this slip transistor and the leakage current of this power gated block, and also the L by W ratio and various other parameters that I have discussed. So, what can happen, this the output of a power gated block can have some intermediate value, and that intermediate value can lie in the range of that it may be greater than VTN, that is the threshold voltage of the NMOS transistor, and less than VDD by VTP, that is your VDD minus VTP, where VTP is the threshold voltage of the PMOS transistor. In such a case, what will happen? As you know, in such a case, this voltage will lead to what is known as short circuit current or crossover current. So, the input voltage here is such that this transistor as well as this transistor both are on. As a result, current will flow through this part of the circuit. I mean, short circuit current will flow, or crossover current is flow, that is another name of short circuit current that can flow through this part of the circuit. Question is, how can it be stopped? How can this short circuit current can be prevented? To prevent this, you have to use what is known as signal isolation. So, you have to isolate this power gated block with the power up block. You have two types of circuit present in a circuit in operation. Some part will be power gated, some part will be active. So, there is an interface between power gated block and a power up block. So, what you have to do, you can see here, you have got power gated block, and this is driving a non power gated block. So, if this voltage is not appropriate, if it is not 0 or VDD, then this will lead to short circuit power dissipation, as I have told. So, what you have to do? You have to add additional hardware, and this is known as isolation hardware. Why do you need it? Because as I told, there is no guarantee that the power gated blocks will fully charge or discharge. So, the output of a power gated block is clamped to low or high or to the most recent value to prevent crossover current in the powered up blocks. So, what can be done? You will add some additional hardware in between this power gated block and non power gated block, and what will be the output? Either this will be clamped to low level or to high level or to the most recent value. So, whenever you have to output the most recent value, obviously you will require some kind of memory as part of this hardware, isolation hardware. So, this let us see how it can be done. So, first of all, it is necessary to clamp the output to an inactive state, an AND gate function can be used to clamp the output to 0 level. So, you can use just an AND gate. So, this is the output of the non power gated block, that is isolation control signal. So, here it is coming from that power gated block. So, power gated block input is coming here, and this output will be clamped low irrespective of this input here. If this input is 0, this output will be 0. That means, when this particular this signal is low, that means you have done power gating, then what will happen, this output will be this will be clamped to low level. Similarly, you can use an OR gate. In this particular case, this output will be clamped to high level. That means, irrespective of the inputs at this input, whenever this is 1, this will be clamped to high level, and as a consequence that uncertainty will not arise here. An alternative approach is to use pull up and pull down transistors. So, instead of gates, so you know that gates will be having some delays. So, if you want to avoid these delays, you can use simpler hardware known as pull up and pull down transistor. So, here you can see this is the isolation signal and a transistor is there. So, this signal is used here to control this output. So, whenever it is high, this will be clamped down to low level. Similarly, in this particular case, whenever this is low, this signal is low, this will be clamped down to high level. So, you can use this type of simple clamping circuits instead of using gates when delay requirement is large. However, there are some strategies which are used to make the circuit foolproof. So, you have to isolate outputs of power gated blocks, use isolation cells rather than pull up and pull down style clamps. That means, it is being recommended not to use this type of hardware, rather than it is better to use this type of gates to avoid testability problems unless using very specialized protocols. Actually, you have to consider the testability of the circuit, and you have to ensure that stuck-at 0 and stuck-at faults can be detected during testing. So, if you use this type of circuit, this type of testability can be hampered. We are not going into the details, but using this type of circuit, that testability can be ensured by applying proper signal here, but which cannot be done in this particular situation. So, make sure that all isolation cells are always powered up. Another important thing that you have to remember, this additional hardware should be always powered on. That means, this power supply of this should not be clock gated, it should not be gated. So, should not be power gated. So, they should get continuous power supply. So, this is the isolation strategy. Now, coming to state retention strategy. So, given the power switching fabric and an isolation strategy, it is possible to power gate a block of logic, but unless a retention strategy is employed, all state information is lost when block is powered down, as I have already discussed how it happens. And to resume its operation on power up, the block must either have its state restored from an external source, as I told the device driver can do it, or built up its own state from the reset condition. So, there may be some built in hardware. So, in either case the time and power required can be significant, and there are 3 basic approaches. First one is known as a software based approach on reading and writing registers. Second is scan based approach based on reuse of scan chains to store state of chip, and register based approach that uses retention register. Let me very quickly go through these 3 techniques. In the software based approach, you have got a always on CPU. So, what you are doing here, a program is running which will whenever you have decided to power down a particular block, their states will be saved, will be transferred to some internal registers of the CPU by programming, and during power up sequence the CPU writes back the registers from the memory, or you can store them in the memory, either in the register or in the memory. So, bus traffic slows down the power down and power up sequence. However, whenever you do that, the activity this storing and loading will take place through the system bus, and this will definitely influence the traffic on this bus, and bus conflicts may make power down unviable. So, there may be bus conflicts, and that may lead to unviability of this approach, and software must be written and integrated into the system software for handling power down and power up. So, you have to write appropriate software which will take care of this. Second approach is scan chain based. You know, nowadays you are using built in self test. So, built in self test technique requires some additional resistors for inputting the test sequence and outputting the response, and these are the resistors which are used at the time of testing, built in self test. Those resistors can be used to store the states of the those blocks which you intend to put to sleep condition. So, scan chains used in the BIST can be reused, and during power down sequence the scan register outputs are routed to a on chip or off chip memory, and this may lead to significant saving in significant saving, because you are not using any additional hardware. The scan chain registers are being used to save the state of those blocks which you intend to do power gating. Third approach is based on retention registers. As I was telling, you can have built in hardware present inside those blocks. So, what is being done, you have got two sets of resistors, one is master, another is slave. So, whenever you have a slave signal is received, the information is transferred from the master to the slave. So, and whenever again when resto signal comes, the information is transferred back from the slave to the master. You may be asking, that means whenever you are in the power gated block, this part is switched off, not this part. That means that is the reason why you have two power inputs. So, this is the VDD switched gated. So, the master will receive this switched power, and on the other hand this slave registers will require non gated power, because they have to store the information. Now, this will require additional control signal coming from the controller. So, save and restore. So, before going to low power state, you have to save, and before you wake up you have to restore. These signals are generated. However, you can use a single signal retain, that means when depending on whether it is 1 or 0, you can either retain or you can transfer to the master. You can do it this way, and these retention resistors are realized by using high threshold voltage transistors, and as a consequence the power dissipation in these resistors is quite small compared to the leakage power that takes place in these masters. So, in addition to area penalty, you have got more complex power controller is required, because these signals are to be generated from the power controller. Let us now coming to the power gating controller, So, a key concern in controlling the switching fabric is to limit the inrush of current when power of the block is switched on. An excessive inrush current can cause voltage spikes on the supply, possibly corrupting resistors in the always on blocks as well as retention resistors in the power gated block. So, one representative approach is to daisy chain the control signal of the switches. The result of this daisy chaining is that it takes some time from assertion of power up signal until the block is powered up. So, a more aggressive approach to turning on the switching fabric is to use several power up control signal in sequence. So, regardless of the specific control method, during power up sequence it is important to wait until the switching fabric is completely powered up before enabling the power gating block to resume normal operation. So, this is the requirement of the power gating controller, and let us have a look at the activity profile whenever you do the power gating. As you can see, you are ramping down the supply and ramping up the supply. You are not abruptly changing the supply voltages, and this is the activity profile with realistic power gating. and the power gating controller, which is will generate the sequence. When power gating has to be done, you can see the signals are generated, control signals are generated in sequence. First you are doing isolation signal, then you are doing reset after it has been isolated, then you are doing power gating, that means the switches are turned off, and now during this period the circuit is in power gated condition. Similarly, you have to deassert in the reverse sequence, that means for the power switch is turned on, then you are doing the reset after it has stabilized, then you will isolate, deactivate the isolate signal and start the clocking. So, first thing you have to do is to stop clock, and you have to follow this sequence when you go to low power mode, and this is the sequence you have to follow when you come back and when you wake up, when the circuit wakes up. So, this can be done with retention also, only difference is that you will require two additional signals, as you can see, save and restore, rest of the thing is same. When you go to low power mode, you have to use this additional signal save before you reset the hardware, and similarly as you before you wake up, you have to restore the resistors after turning on the power, then you have to apply the deassert the signals in the reverse order, first the power of the hardware, then apply reset signal, then isolate the signal, then apply clock. So, this is you have to follow this sequence. Now, whenever you are using this approach, you are essentially that power management unit controller is interacting with the switches. The switches can have different delays and other thing depending on the realization, actual realization. So, they can have variable delays. So, to take care of variable delays, you can work in a kind of asynchronous mode, in which case there is a kind of handshaking, as you can see. After isolating, you will generate the reset signal, then the request is sent to the switching fabric for power down. Obviously, the switching fabric will take some time to power down, it will do the it will switch it off, then send an acknowledgement signal. Similarly, as you request, whenever you have to turn the power on, you have to send a signal to the switching fabric, and switching fabric will take some time to turn on, and it will send a signal to other parts of the circuit. It will generate the reset signal, it will isolate, and then finally clock is turned on. So, you have to it has got built in interlocks and synchronization to ensure safe wake up sequence. So, we have discussed the power gating technique in detail, the various issues involved in power gating we have discussed in detail. In the next lecture, we shall discuss other techniques for minimizing leakage power. Thank you.